In the video for 28A, we developed a sort of plan, a sort of description of the journey that a ketone takes when it becomes an acetal. Now in this specific example, we have acetone, so you might use that as nail polish remover. It's the simplest ketone, and we're treating it with two equivalents of an alcohol, like we did in the previous three mechanisms. But interestingly, the two equivalents of the alcohol are on one molecule. So instead of needing separate molecules, we can form this acetal with just one. This is two alcohols that we can add. And you can see that the acetal that we'll get will be formed with those two adding separately to make that cute little molecule on the right that we have here. Now, you know that this is an acetal because you have a carbon that's bonded to ethers, two ethers, one on each side. So the same carbon has two ethers, that's an acetal. And we do that by adding two equivalents of alcohol here on the same molecule. You'll notice that we also add catalytic acid. We have H2SO4 there, and that's in the brackets, which with this textbook means that it's catalytic. But we put that into water, and instantly the sulfuric acid, which is a very strong acid, gives away all of its H's, H pluses. And the real acid we're going to have in solution, the effective acid, is going to be hydronium. So that's going to be our acid catalyst here. Now in between the ketone and the acetal, one of the alcohols will add. So we'll have one of the alcohols adding, but the other would not have added yet. And the carbonyl carbon will turn into an alcohol. This is what our hemiacetal will look like in this particular case. You'll notice we added one of the OHs, and then the carbonyl carbon, or the carbonyl oxygen, is now this OH. So our hemiacetal. Okay, so that's our general plan. This is our general idea. We're going to use these overall molecules, and we're going to follow our flowchart that we built before. Going from the ketone to hemiacetal, the process is bookended by proton transfers. In the middle, we have a nucleophilic attack because we have to add something onto the molecule. Going from a hemiacetal to an acetal, the process is bookended by proton transfers. We have to make the OH leave, so loss of a leaving group, and we have to bring the other alcohol on board, so nucleophilic attack. Okay, so let's draw this out for these specific molecules. We have acetone. Interestingly, you could very easily do this reaction at your house. Acetone you can buy at like a beauty supply store, and this molecule is ethylene glycol, which is car antifreeze. So you have this. We're going to turn this into the carbonyl carbon here, and it's a good electrophile. It's double bonded to an oxygen, so it's losing a lot of electrons that way. But we want to turn it into an amazing electrophile because the alcohols that we have don't have any charge. The alcohols that we have in this ethylene glycol molecule are neutral, so they're not the best nucleophiles. So we need to make the electrophile amazing in order to tempt that nucleophile to react with them. And we do that by adding a hydrogen, by doing a proton transfer. Now, we have some hydronium ion. Here, the oxygen in the acetone is slightly negative, and the hydrogens in the hydronium ion are slightly positive, so that oxygen can attack one of those. The electrons going to the hydrogen snap back onto the oxygen, help to stabilize the positive charge there. And so that forms an amazing electrophile. And this is such a good the carbonyl carbon is such a good electrophile because not only does it have these two bonds to this oxygen, which is really electronegative, but the oxygen has a full positive charge, so it uses that power to really pull electrons to itself. and the carbon has almost a full positive charge. And we saw in the video for 28A, 20.8A, we saw how you could also use resonance to describe how you get a better electrophile there. Okay, well, we also formed water. The hydronium turns into water after it loses its H+. Well, now we have such an amazing electrophile that even our weak nucleophile can attack it. The slightly negative oxygens, one of them, they're both slightly negative, one of those oxygens can act as a nucleophile and attack the carbonyl carbon. The pi bond, which is easier to break because it has interrupted overlap between those parallel p orbitals, the pi bond breaks, the electrons go onto the most electronegative place nearby, that's the oxygen, and it helps that oxygen to stabilize the positive charge there. So now what we have is we have this ethylene glycol. The oxygen that attacked still has its hydrogen on it, has those two carbons, and then another OH on the molecule. This one here has a full positive charge because it's an oxygen with 3 bonds, and that, the carbonyl here, ends up turning into an alcohol. Right, the OH, but just with a single bond now. Well, we're really close to having the hemiacetal. We just need to stabilize this positive charge. So we can take the water that we produced in the previous step and use that as a base. The slightly negative oxygen in the water will steal the slightly positive hydrogen on this, and the electrons will go to the oxygen to help stabilize that positive charge. So what we have now is the hemiacetal. We've added one of our alcohols completely. So this is our hemiacetal. We're halfway to the acetal. Okay, well, where do we go from here? We have to kick our leaving group off. Right now we have a bad leaving group, the OH. That would just leave us hydroxide, which we know is a strong base, strong nucleophile. So that would just snap right back on. So we have to turn that into a good leaving group by doing a proton transfer. So we can take the H3O+ that we formed in the previous step. When this water stole this hydrogen, it formed this hydronium. We can take that, and the oxygen here in this leaving group can steal the slightly positive hydrogen. The electrons snap back onto the hydronium ion, oxygen. So that's our proton transfer. And when we do that, we turn a bad leaving group into an amazing leaving group. So the OH, which is a bad leaving group now, is basically H2O. And that's very willing to pop off of that molecule. All it needs is a little push, and the leaving group will leave. Let's move this down here just for a little extra room. Well, the slightly negative oxygen here has been eyeing the slightly positive carbon here for the whole time. It's constantly trying to form a new bond there, but the other group has always gotten in the way. Well, now the other group can leave, and so these electrons go to push to form that pi bond there, and that knocks the leaving group off the molecule. So now we have that water that got kicked off of the molecule, and we have this new compound here. Now this oxygen has 3 bonds, so it has a full positive charge. And an interesting thing happens here. This molecule should look weirdly familiar. It should look like what we had in the very beginning. Remind you of this a little bit. When we made that awesome electrophile, we had this sort of oxonium ion, oxygen double bonded in a carbonyl compound, but then a single bond to something else. Now here it was to a hydrogen. In our new thing, it's to a weird group. But we still have, the point is, we still have in that whole thing, we have an amazing electrophile in that carbonyl carbon. It's losing its electrons to the electronegative oxygen through 2 bonds, and the oxygen is super electronegative because it has a full positive charge that it can use to attract electrons to itself. So the carbonyl carbon is really low in electrons, and this oxygen right here has a slightly negative charge. Well, it doesn't take much for that nucleophile to attack your electrophilic carbonyl carbon. That pushes the electrons in the pi bond onto the oxygen to stabilize the positive charge. So that's, here we had loss of a leaving group. Now we're showing nucleophilic attack. After this attack, the oxygen that was already there only has a single bond to it. You'll have the 2 carbons, the other oxygen, which now has another bond to it, but that still has its hydrogen. This didn't go anywhere. So this oxygen on the right has a full positive charge because it has 3 bonds. And all we have to do is stabilize that positive charge with a proton transfer, and we have our acetal. So we need a base. The base can be the water that we made last time. Slightly negative oxygen steals the slightly positive hydrogen. The electrons ricochet back onto the oxygen to stabilize the net positive charge there. And we are left with our very interesting looking acetal. And you know this is an acetal because you have an ether bonded, 2 ethers bonded to the same carbon, coming off of the same carbon. So that's an acetal. Now, one thing that's kind of interesting to note, this looks really strange, but this ethylene glycol is actually used a lot in synthesis of ketones because it protects ketones. We'll see throughout this chapter, we'll see all the other reactions you can do with a ketone. Sometimes you want one ketone to react, but you don't want another one to react. And so what you can do is you can use this ethylene glycol and you can cap the ketone. You can turn it into the acetal. So you can react it with the ethylene glycol, you'll get the acetal, and now this is not going to react in the same way as another ketone on the molecule may. So you can sort of protect a ketone by putting this acetal on it. Then ethylene glycol is a useful one because it forms a discrete molecule. Remember again, in these you have some sort of a ketone and you end up forming the acetal, and you also end up forming water. Right? The 2 H's here and the O in the carbonyl go to form the water. And this is an equilibrium reaction, so it obeys Le Chatelier's principle. And you can think of Le Chatelier's principle as a sort of water tank where the left side of the reactants and the right side of the products. You can control the flow of the water or the flow of the equilibrium by either adding more reactants or products. If you want to protect the ketone, all you have to do is heat up the reaction a little bit, and that'll remove products. Well, if you remove products, like opening a hole in the water tank, then the water flows to the right to resist the change. So the ketone would turn into more and more of the acetal. On the other hand, what if you protected the ketone, you did the reaction with the other carbonyl compound, and now you want the ketone back? Well, then all you have to do is dump water in there, add a product, and the water flows to the left side of the tank to resist the change in equilibrium. And so you get the ketone back. So you can use Le Chatelier's principle to control the direction of, if you notice, every step in this is an equilibrium step. And so the overall reaction is an equilibrium reaction. And you can control what you have more of, either the ketone or the acetal, by either heating it up to remove water or pouring water in. That's adding a product, and that would give you more of the ketone. So this looks like a really weird example, but actually it's one of the most common acetal examples that people use in chemistry labs, because this is able to protect ketones really well. It's very easy to put it on and to take it off just by using water and heat and Le Chatelier's principle. Okay, let's do one more of these. We'll look at the mechanism for acetal formation here. kind of another cool looking one. It looks strange, but really it's the same principles we've been using this whole time. We have a ketone, so we have our ketone really in the middle of this larger molecule. And attached to the very same molecule, we have both of our alcohols. Right? The alcohols are on the ends. So they're not separate molecules. This is going to be an intramolecular acetal formation. So the acetal we get at the very end, the alcohols replace the carbonyl. And you can tell that that's an acetal because you have a carbon that has ethers, 2 different ethers bonded to it. Now halfway in between, only one of the alcohols will add. So what you'd get is, one of the alcohols are adding, but the other one, the other position, stays as an OH, and the other alcohol has not added yet. So this here, that's from this. This OH is from the carbonyl oxygen that really hasn't left yet. Okay, well this looks strange, but really it's the same exact steps, the same journey that we've traveled many times before to go first from the ketone to the hemiacetal, and then from the hemiacetal to the full acetal. So let's go one step at a time. Remember, to go from the ketone to the hemiacetal, it's a process bookended by proton transfers. We're adding the alcohol, so we have to do a nucleophilic attack. For the process to go from the hemiacetal to the acetal, it's a process bookended by proton transfers. In the middle, we have to remove the OH, so we do loss of a leaving group, and we have to add a second alcohol, and so we do nucleophilic attack. Okay, let's draw it in. Well, we only have one molecule here, it's this thing. Oops. So that's our starting material that they gave us. And we have a nucleophile built into the molecule. This oxygen is definitely slightly negative, and it would love to attack the electrophile in this molecule, but it's not the best nucleophile. This is just a slight negative charge, not a full one, and so to make the reaction happen more efficiently, we can turn our electrophile into a better electrophile by adding acid, doing a proton transfer. Now they give us catalytic sulfuric acid. This textbook uses those brackets to express a catalytic acid. But you put that sulfuric acid into water, and it gives all its H pluses away. And really, the acid you have in solution is hydronium, H3O+. So the slightly negative oxygen in the carbonyl, in the ketone, can attack the slightly positive hydrogen and kick its electrons onto the oxygen to help to stabilize that positive charge. So that's our proton transfer. And when we've done that, let me actually do this. Once we've done that, this oxygen will be bonded to another hydrogen. So that gives it a full positive charge. And when we have that, the power of this electrophile becomes intense. Because now it's not just losing electrons to the oxygen because the oxygen is electronegative, but the oxygen sort of has a superpower. It has a full positive charge with which it can attract electrons even more. And so the carbonyl carbon loses these electrons, that electron density, and becomes really slightly positive. So now it's an immensely powerful electrophile. The nucleophile now can swoop in and attack and kick the electrons onto the oxygen where they can stabilize the positive charge there. So that's our nucleophilic attack. Now when it does this, it's going to form a ring. So we're going to have that same motif. We'll still have 4 carbons there, but the oxygen will be attached to that carbonyl carbon. It still has a hydrogen on it, and because it has 3 bonds, it has a positive charge. we will also have an OH on that ring. The OH is coming ultimately from the carbonyl oxygen. The rest of the molecule did not participate just yet. And so that is almost our hemiacetal. We just have to stabilize this positive charge, and we can stabilize it by using the water that we formed from this first reaction. That hydronium ion lost an H+ to form water. Well, now the water can come back and act as a base. It can steal the slightly positive hydrogen, and the electrons ricochet back onto the oxygen to help to stabilize that positive charge on it. So after this step, after this proton transfer, we end up with the hemiacetal. We also get hydronium here. So this is your hemiacetal. Because we have an ether and an alcohol on the same carbon. Well, we're halfway there. We just need the OH to leave, and we need the other alcohol to come in and attack. And right now this is a terrible leaving group. To make it a better leaving group, we can do a proton transfer. So that slightly negative oxygen in the alcohol can attack the hydrogens in the hydronium we made. The electrons can go back onto the oxygen there to stabilize the positive charge. So there's our proton transfer. So we're going to have this same molecule, but these lone pairs will now be a bond to a second hydrogen. This oxygen has 3 bonds, so it has a full positive charge. And now it's an amazing leaving group. All it needs is a small push, and the leaving group will leave. The push comes from the lone pairs on the adjacent ether. That oxygen is slightly negative, and it's been eyeballing the carbonyl, well, what was the carbonyl carbon this whole time. This carbon is bonded to 2 oxygens, so it's slightly positive. It's losing its electron density in 2 places. So that it attracts those electrons next door. Those snap in to form a pi bond, and they kick off the leaving group. So what we form is that oxonium ion, water is left, and then the rest of the molecule is here. Okay, well, in its own weird way, this should remind you a little bit of what we had sort of at the beginning. We have that carbonyl compound with a third thing coming off of it, so the oxygen has a full positive charge. And that made the electrophile amazing. So here we have the same sort of feature. Carbonyl with a third thing coming off of it. But the third thing is a carbon chain instead of the hydrogen. So the carbonyl carbon here has a huge positive charge, both because it's bonded to oxygen twice, but also the oxygen has a full positive charge, so its ability to attract electrons is much, much bigger. And this carbonyl compound is now an amazing electrophile. It's able to attract even the weak nucleophile of the alcohol. That swoops in, and here actually I'll use the other side, swoops in, attacks that, kicks the pi bond onto the electronegative atom nearby, that oxygen. So that's nucleophilic attack there that we're doing. And the result of that step is that the pi bond is no longer there. It's now another lone pair. And this oxygen, this alcohol, is going to be attached to the ring. And it still has its hydrogen, nothing happened to that, and because it has 3 bonds, it has a full positive charge. So we have our nucleophilic attack, so we get this. And we're almost there. We almost have the acetal. We just have to stabilize that positive charge with a proton transfer. So we can use the water that we formed earlier as a base. The slightly negative oxygen can steal the slightly positive hydrogen. The electrons snap back onto the positive oxygen to help stabilize that charge. And you have your final acetal. And you know it's an acetal because you have a carbon that has an ether on both sides. It has bonded to two ethers. So that's our beautiful, very cool, kind of strange, but fascinating acetal. And the mechanism is really the same as what we've been doing this whole time. But it's interesting to see those same steps applied to an intramolecular reaction. And it's also an important thing that often happens in living things. You'll have lots of functional groups on one molecule, and the molecule can react with itself. Okay, so hopefully this helps you to see a couple variations of the mechanism for forming acetal.